For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at https://www.computernetworkassignmenthelp.com. Problem 1. Leader election in a synchronous ring. Consider a collection of n identical processes arranged in a synchronous ring network. Each process has two sets of ports, one to each of its immediate neighbors, with its ports to its clockwise neighbor named left and its ports to its counterclockwise neighbor named right. Thus, the processes have a common sense of orientation. The goal is for the processes to elect a single leader. Exactly one process should eventually output leader. A. First, suppose that the processes are deterministic and that they know n, the size of the ring. Either give a correct leader election algorithm for this case, or prove that no such algorithm exists. If you give an algorithm, analyze its time and message complexity. Solution: impossible. Suppose for contradiction that such an algorithm exists. We can use a standard inductive symmetry argument. Namely, prove by induction on the number r of rounds that, after r rounds, all the processes are in identical states. Since the algorithm must solve the leader election problem, eventually, one process outputs leader. But then all processes do the same thing, in the same round. ComputerNetworkAssignmentHelp.com. B. Now suppose that the processes are probabilistic, i.e., randomized, and that they know n. We would like an algorithm that A. Never elects more than one leader, and B. With probability 1, eventually elects a leader. Either give an algorithm satisfying these properties, or prove that none exists. If you give an algorithm, analyze its time and message complexity. Your analysis should relate the complexity to the success probability. Specifically, for any epsilon 0 epsilon 1, you should provide bounds on the time and message complexity that hold with probability at least 1 minus epsilon. Solution: here a simple algorithm exists. Lemma, similar to one from class. If n processes choose IDs uniformly at random, independently, from 1 to n2, then with probability at least 1/2, the chosen numbers are all distinct. Algorithm. The algorithm works in a series of phases. In each phase, all processes choose random IDs from a sufficiently large space, defined as in the lemma as 1 to n2. Then they all send their IDs around the ring, say, in the clockwise direction. After exactly n steps, every process examines the sequence of IDs that it has received. There are 3 cases. 1. If the maximum ID in the sequence is not unique, it abandons this phase and goes on to the next. ComputerNetworkAssignmentHelp.com. 2. If the maximum ID in the sequence is unique and is the process own ID, then it outputs leader and halts. 3. If the maximum ID in the sequence is unique and is not the process own ID, then it just halts. It should be clear that, at the first phase where all the processes choose distinct IDs, exactly one process elects itself the leader, and then the algorithm halts. So certainly the algorithm never elects more than one leader. At each phase, with probability at least 1/2, all the chosen IDs are distinct and the algorithm terminates. Since the choices in different phases are independent, the probability that the algorithm finishes within h phases is at least 1 minus 21h. Thus, with probability 1, it eventually finishes. We analyze the time and message complexity. Each phase consists of n rounds, and sends N2 single-hop messages. Consider any epsilon 0 epsilon 1. Choose h to be the smallest integer such that 21h less than or equal to epsilon, that is, h equals ilg 1/epsilon L. Then with probability at least 1 minus delta h greater than or equal to 1 minus epsilon, the algorithm finishes within h phases, using nh rounds and n2h messages. That is, with probability at least 1 minus epsilon, the time complexity is at most nilg 1/epsilon L and the message complexity is at most n2 ilg 1/epsilon L. Computer Network Assignment Help.com. C. Finally, suppose that the processes are probabilistic and they do not know n. That is, the same algorithm must work regardless of the size of the ring in which the processes are placed. We would again like an algorithm that A. never elects more than one leader and B. with probability 1, eventually elects a leader. Either give an algorithm satisfying these properties, or prove that none exists. If you give an algorithm, analyze its time and message complexity as described in Part B. Solution. This is impossible. Suppose for contradiction that such an algorithm exists. Consider the algorithm operating in a ring S of size n, for any particular value of n. Number the processes of S as 1, and based on their positions in the ring, counting clockwise. Since the algorithm eventually elects a leader in ring S with probability 1, there must be at least one execution alpha of S that leads to some process J outputting leader. That is, there is some particular mapping from processes to sequences of random choices such that, in the execution alpha in which these choices are made, some process J is elected leader. Now consider a ring R of size 2n consisting of two half-rings R1 and R2, each of size n. Number the processes of R as 1, 2n. Then there is an execution alpha of R in which processes I and n plus I in R happen to make the same random choices as process I in S. In execution alpha, processes I and n plus I behave exactly like process I in execution alpha of S. Since process J outputs leader in execution alpha, both processes J and n plus J output leader in execution alpha. This contradicts problem requirement A. Notice that this proof shows that we can't achieve any positive election probability epsilon, not just probability 1. Computer Network Assignment Help.com. Problem 2. Breadth first search in an asynchronous network. The asynchronous breadth first search algorithm presented in class involves corrections that could trigger the sending of many messages, resulting in worst-case message complexity O in E and worst-case time complexity O diam ND, until all nodes' parent variables have stabilized to correct parents in a breadth-first spanning tree. We are not considering individual processes' parent outputs here, nor global termination. We are also ignoring local processing time. This problem involves designing a better asynchronous breadth-first search algorithm, one that does not make any corrections. Thus, once a process sets its parent variable, it can output the value since that is its final decision. Assume that the network graph is connected and contains at least two nodes. A. Describe carefully, in words, an algorithm in which the root node V0 coordinates the construction of the tree, level by level. Your algorithm should take time O, diam 2D, until all the parent variables are set. Hint: the root node can conduct broadcast convergecast waves to build the successive levels in the tree. 4 types of messages should be enough. Example: search messages that test for new nodes, parent, B, BA Boolean, for parent/non-parent responses, and ready and done messages for broad